6. This is Ms. Stone here, and we're going through the lesson on atmospheric pressure. So we talked about pressure being force divided by area. Atmospheric specifically is like the force, the weight, the gravity force of all the air on top of us. That's what it is. If we measured it pounds per square inch, which is the an imperial way of measuring it, that literally is the pound force of gravity per square inch on your body that you're feeling, okay? For us, it's newtons per meter squared, right? That's what a Pascal is. And so it is not the weight of the world, it's weight of everything above the world, okay? And that's what we feel. So for the atmospheric pressure is 101 kilopascals, about that. So we actually feel then all the time 101,000 newtons per square meter of our body, which probably our body has a surface area of about a square meter. That's actually an interesting question. But anyway, that's atmospheric pressure. So at sea level, like I say, it's about 101,000 pascals. The Denver Broncos, who I don't know if they played at home tonight, but I do know they beat the Buffalo Bills, which was very nice. They just finished playing at 7 o'clock. Anyways, up there though, you may have noticed if you watch a football game or something in Denver, that sometimes they need oxygen. It's because it's significant. It's 20% less pressure there, which really means, because we're talking about the weight of the air, so that means in a way there's 20% less air, right? 20% less oxygen. If you got as far as the top of Mount Everest, then we're looking at 30 kPa. And being up in these atmospheres, like even this, but more likely for something like Everest, you do get something called altitude sickness, right? And there's all these things that, makes you feel terrible because you have less oxygen, right? And that's why the guys at the football game, I say guys, not being sexist, but NFL players are. Anyway, so the concept of atmospheric pressure, of course, is built into a lot of pieces of machinery that we use, like a straw. And in a straw, you get this idea, it creates a vacuum. What happens is your mouth sucks in, so you suck in and you create a zero pressure area inside your mouth. So you're not actually pulling up the fluid. What you're doing is creating zero pressure in your mouth so that the atmospheric pressure is pushing your root beer into your mouth, right? So you're not actually pulling it up. The atmospheric pressure is pushing it up. All you're doing is creating zero pressure inside your mouth. You're creating a place where it's easier to go, because things tend to move from high pressure to low pressure. So different ways you can measure pressure, or somebody measures pressure. You may never do this on your own, but there's something called a barometer, and a barometer is a tool used to measure pressure. And it does look something like this, and it's done with mercury. And that's why one of the standard measures of pressure is, atmospheric pressure is called 29 inches of mercury. Okay? And what that means is you set up a device that looks like this. It has a vacuum at the top. And so that's sort of, it's closed in, it's designed to be a vacuum. And then you have it open down here to air pressure, filled with mercury, and based on the density of mercury. Air pressure pushes down on this. Oh, I have that there. Air pressure pushes down, and that causes the mercury to move up. And you can measure how much pressure so we have a basic gauge of where it would be if there was 101,000 kPa. And on a high pressure day, I don't know if you knew that you probably know this from sort of just listening to the weather and that. They'll say it's a high pressure zone, low pressure zone. High pressure is associated with bright, clear, crisp days. And that means there's higher pressure. So this number might be 102, 103 kPa. And if it's a low pressure day, like it's going to be stormy, that's a low pressure day, which kind of makes sense because on a low pressure day, it's like it's pulling in the weather. The low pressure is like a vacuum pulling the weather in, the clouds and the rain. Anyway, but the idea is that pressure pushes the mercury up, so you have an idea of where it should be. So if it's a 101 kPa, it's calibrated, that would be at a certain point. And then if it's a high pressure day, it'll be higher than that point, and if it's a low pressure day, it'll be lower than that point. So, and that's sort of similar to what I'm saying. You don't actually measure 101 kilopascals or whatever. but you're measuring something and you're comparing it to what we call the gauge. Gauge pressure is sort of the difference between atmospheric and what the actual pressure is. And we might hear about that inside some sort of vessel. I know when I worked at 3M in London, I always dealt with air pressure, air cylinders. Of course, and they're operating under high pressure. So we might care about the pressure in that cylinder, or even your tire, for heaven's sake, right? Lots of applications of where you have something where you measure the pressure. And usually you're not measuring, the actual pressure. You're measuring how much above or below. You're measuring gauge pressure, how much above or below atmospheric it is. So if I read the gauge pressure in this vessel be 10, that would mean that the absolute pressure would be 111. That's the difference. If it was -5, then the actual pressure would be 96. That sort of idea. So there's the formula. Another way to measure pressure, kind of the same idea, is using something called a manometer. And what it is you've got, so this sort of would be connected to some high pressure zone. And this could be, pressure was the biggest deal when I worked as an engineer. And I worked at 3M. And we would be sending fluids through pipes all the time. And of course, it's pressure that drives that, right? And so to measure that pressure, and when I say fluids, that could be the solvents that were used in the adhesive itself, whatever we're using. But you'd have sort of a manometer that would be, and it'd be more high tech than this, but it would be connected to your what we call the high pressure zone. So say in your pipe, the other side would be open to atmosphere, and then based on sort of how much this fluid, and you choose this fluid. Okay, it could be water, for example, and the density of water based on how much difference there was in the two heights here. You could say how much pressure, right? Because if this is a bigger distance than this distance, you could calculate, and this is the formula. So you need to know the density of this fluid, and you need to know this difference in height. So from here, this height distance to that height distance. And sometimes they call that the a pressure head or something like that. Like they'll use the word head, H, but it's height. That's all it is. So just to see an example. So an air pump is connected to one tube of manometer containing water. The static pressure head, which like I say, that's the H, is 0.15 meters. Determine the gauge pressure. So gauge pressure, and I guess I just drew a picture of this, like this is basically what I'm saying, is I've got, that should be over here. So this is the part that's connected to my air pump, okay? So the gauge pressure is 1,000 times 9.8 times 0.15, so DGH, pretty easy, right? So I get a number in pascals. And then it says, well, what's the absolute pressure? Well, that's just going to be the atmospheric, which is 101,000. That's just a given, plus 1470. And that's the actual pressure inside the air pump. Okay, another good question. The absolute pressure at the bottom of my swimming pool. So the depth is 2 meters. What's the pressure down there? Well, the absolute pressure would be the pressure, this is like, the PG is like the pressure due to the water, okay, at the bottom of the pool, and this is the atmosphere pushing down on it. So it's the 101,000 plus DGH, and then you use D, height's 2 meters in this case. So it doesn't have to, that equation doesn't have to apply to a manometer, it could apply to anything, water under a certain depth, okay? The question I always use is the Titanic. I always think about, if you don't know, did you watch Titanic? I love the movie Titanic. So, remember when they had the little vessels looking around, and they were those circular vessels, and of course they have to be so thick because the water pressure at the bottom of the Atlantic there is so high, right? So 13,000 feet below, I wouldn't ask you to do this for me. You'd just use a unit converter would do it though. So in fact, if I went 13,000 feet in meters, I could just Google it. 13,000 feet, 3962. So Google does everything, right? So it tells us how many meters that is, okay? So we have our meters, and then to calculate the absolute, you add the 101, the air pressure, but it's pretty minimal compared to all this, okay? So the water, it doesn't say, but you should, if you're given at some point on your test, you're given, or if you're working on questions where I haven't given it to you, you would have to know that water is 1,000. You'd have it, like I would tell you it the first time, but if even it's not on this particular question, I'd expect you to know that we're talking about water. And so you'd have to use 1,000. Okay, this activity, I'm looking to see you do this one in class. And the idea is this: you take a can, and you're going to pierce 3 holes in it, and try to be safe about it. Then you're going to pour water into that can, and before you do it, and then after, I want you to predict, what do you expect the streams of water to look like? And how does it apply to what we were just talking about? So it's going to look like one of these 3 patterns. Which do you think it's going to be? And maybe with an explanation why. So I'll look for you to do that one, and tell me what you think. I think that's it for this lesson on atmospheric pressure.